Let's talk about climate change. People are calling it the crisis of our time, and it is.
Climate change.
Climate change.
Climate
Changes.
Climate change.
But it's easy to get lost in this story. The science is dense and politics get in the way. World leaders are meeting in Madrid to talk about the climate crisis and how to slow it down. And they're under pressure from millions of people around the world calling for concrete action.
The empty promises are the same, and the inaction is the same.
So what exactly are we doing wrong, and how do we fix it? We're going to kick this off with some basic science, so bear with me, because this is important. Look at this graph. These are the levels of carbon dioxide in our atmosphere over hundreds of thousands of years. But this spike in carbon dioxide at the very end, that took off during the Industrial Revolution. We started breaking CO2 records in 1950, and we haven't stopped since. Why? Well, scientists say there's a 95% chance that human activity is the cause. We've been burning more and more fossil fuels like oil and coal, which release CO2, to power our homes, factories, airplanes, and cars. There's also a lot more of us. The global population has tripled in the past 70 years. And we're consuming more products from animals that release another pollutant called methane. So all those gases are released into the air, and when sunlight gets into the Earth's atmosphere, some of the heat gets trapped and the planet gets warmer. That's why they call it the greenhouse effect. But the concern is not that the Earth is getting warmer. It's that it's happening far too quickly.
But it's actually the warmest temperature on Earth since the last ice age, since 10,000 years ago.
The UN says that right now, our world is about 1 degree hotter than pre-industrial times. That's around the year 1800, which is okay. In fact, the UN says if we warm by 1.5 degrees before the end of the century, we should be fine. The UN even says 2 degrees would probably be all right. But again, the problem is speed, because right now we're on track to hit 1.5 degrees in only 10 years. And if we don't slow that warming down, it could mean catastrophe within my lifetime, and maybe yours too. And we're already getting a taste.
Climate change is here. Climate change is happening. We are well into the 6th mass extinction event.
Europe is currently colder than the Arctic.
More than 1,000 people being rescued just in the early morning hours of Sunday.
Millions of people are likely to suffer worsening food and water shortages.
Drought, which is now in its 10th year, is a phenomena that's here to stay.
We've never seen a year's worth of rain in less than 7 days.
Sea levels are rising about 3 millimeters a year because seawater expands as temperatures get warmer. Melting ice sheets and glaciers also add trillions of tons of fresh water into our oceans. People around the world are already losing their homes. And if things carry on, millions more of us will have to pack up too. Entire coastal cities could be underwater, we disappear.
land breeze, night. At night, the temperature of the land lowers down more quickly as compared to sea water. Warm air above the sea rises up, creating low pressure zone, which is filled in by the cool air flowing in from high pressure zone above the land.
We are surrounded by air from all the directions. This envelope of air around us is what we call atmosphere. Does air also exert pressure on objects on the Earth? In our previous video, we studied that the liquid exerts pressure in all directions. For example, here we have the water in a beaker. Due to gravity, this water is pulled down towards the Earth. If we divide this water into different layers, then each layer is being pulled down by the Earth. Due to this pull, water exerts downward pressure, and this pressure is uneven throughout. That is, the bottom layer experiences more pressure than the top layer. This is because the weight of water above the bottom layer is more, and the pressure decreases as we go upwards. In fact, we saw that the water exerts pressure in all directions and not only in the downward direction. One more thing that we studied about the liquid pressure is that at any point in a liquid, the pressure is the same in all directions. That is, if I take any point here in this water, the pressure exerted by water here is the same in all the directions. Air also behaves in the same way. Just like water, air is also being pulled down by the Earth's gravitational force. This force applies pressure on the air in the downward direction. The pressure exerted by air is called air.
Have you ever heard of upwelling in the ocean and how the Coriolis effect and the Ekman spiral have a huge part in it? No? Well, you're about to. We'll start with the basics. What is the Coriolis effect? Well, it's a term used for the movement of objects that veer right in the northern hemisphere and left in the southern hemisphere. But what does that exactly mean and how does it work? Think of trying to draw a straight line on a sheet of paper. Easy, right? But what if the paper is turning beneath you? Not so easy, is it? This is what happens when the wind is trying to go straight, but the Earth is rotating beneath it. Now that you understand the Coriolis effect, the Ekman spiral will be a piece of cake. Picture wind trying to blow north. Due to the Coriolis effect, it will change directions to the east. On water, that wind blowing north will carry the water to the east. And with the continual rotation, the water beneath the surface will blow south. And then the water under that will blow west, and so on and so on. Just like if we were trying to draw a straight line on that sheet of paper that was turning, we would get a spiral, hence Ekman spiral. Very original, Mr. Ekman. So now we just have one more essential piece to learn. What is upwelling? If you were to shrink the ocean and put it in a cup and color coordinate the density levels, you would get something similar to this. Starting with less dense water on the top and the densest water on the bottom, these layers stay pretty well separate, except in some instances, such as upwelling, when the densest water layer on the bottom comes to the top. What? That doesn't even make any sense, but you heard me right. And this is where the Coriolis effect and the Ekman spiral come into play. Here we have our coast in brown, our dense, cold, and salty water layer in blue, and our less dense, warmer, less salty water on top. When the wind is blowing along a coast in the northern hemisphere, the water along the coast is pushed across the ocean. But then what happens? Does it just leave dry land in its place? No way, Jose. The water below that level will come up and fill the void that was created when the surface water was pushed out to sea. But why is that so important? When the water on the seafloor is pushed up to the top, not only is water pushed up, but also a ton of nutrients that make for a ton of productivity in our oceans. I sure hope that cleared some things up. See you later!
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into two main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean's surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect.
This is a video explaining global winds, including polar easterlies, trade winds, and westerlies. Please watch the climate zones video first before watching this video. It will help you understand global winds a little better if you understand climate zones. I've attached a similar sheet to this, a Google sheet, if you want to print it out and draw with me as I go through global winds. A few things I already have labeled. I've got lines of latitude labeled: 0 degrees, 30 degrees north and south, 60 degrees north and south, 90 degrees north and south. I have our climate zones labeled: tropical, temperate, and polar. For climate zones, remember tropical gets direct sunlight shining straight on, so it's quite warm there. The polar climate zones, the light's coming in and hitting more at an angle because of the curvature of the Earth. So our polar climate zones are going to be very cold because of that. So the Earth is warm in the middle and cold at the top and bottom. Because of that difference in temperature across our planet, we have wind. So the cold North and South Pole they are an area of high pressure. Cold air has high pressure. The atoms aren't moving around as much and they're putting more pressure on one another. So you have a high pressure area here and a high pressure area at the South Pole. At the equator, the sunlight's hitting straight on and it causes the air there to be very warm, and the molecules speed up and they're moving really fast. That creates an area of low pressure because the atoms are not pushing on each other very much. I'm going to go ahead and label equator. So you have high pressure here. It's kind of like squeezing a ketchup bottle. So the wind is going from high pressure, trying to fill in the empty space created in this low pressure area. So the wind from the North and South Pole is trying to make it south to the equator. But because the Earth is spinning and the air is warming up on its journey, it's a little bit more complicated than just rushing towards the equator. So I'm going to try to explain that through this video. Let's start at the top. So air at the North Pole is heavy, or I'm saying it's heavy, it has high pressure. Let's say it has high pressure. And so it is sinking. And it is rushing towards south, towards the equator. When it gets to about 60 degrees north, when the air gets there, it warms up a good bit and it begins to rise. And then it fills in this empty space that was created from the sinking air. So you get a convection cell there because of this warming as the air is on its journey south. Same thing down here for the southern hemisphere. The air is sinking down, it's cold, it's moving south to fill in this empty space. And as it gets to about 60 degrees south, it warms up and it fills back in like that. So you get another convection cell down here. I'll move that up a little bit so you can see it. All right, so that is kind of like showing you the lower elevation or altitude air and higher altitude air, what's going on, like if you think of it as a three-dimensional Earth. Okay, now moving on to, let's do the tropical zones next because they're a little bit easier to understand than our temperate climate zones. So at the tropical climate zones, air is really hot and hot air rises. And some of that air is going to move this way and some is going to move that way. When the air gets to about 30 degrees south and north, it is cooler there. So the air will sink and fall like that. So you get some convection currents around the equator. Now let's go to the temperate climate zones. The temperate climate zones are going to be influenced by their friends near to them. So they are influenced by the cold air at the North and South Pole and the warm air at the equator. Since this air is falling right here, it pulls in the air with it in the temperate climate zone. This air is rising, so it influences the air near it, and you get a convection current like that. If you take a look, up here we're going counterclockwise and counterclockwise. The temperate climate zone is the oddball. He's going clockwise, okay? So same for the southern hemisphere. This air is sinking, so it pulls this air with it. And that is our convection cell for the southern hemisphere temperate climate zones. This one is going clockwise, and temperate, we're going counterclockwise. These convection currents throughout the Earth cause deserts and rainforests to be spread out across our Earth. This hot air rises right here from the heat from the sun. And when the air rises, it carries moisture with it. And when that moisture gets higher up in the atmosphere, it cools, condenses, and falls back down as rain. So if you look on the equator, like through Ecuador and South America, past the ocean into Africa and Asia, you'll notice a lot of green. And those are rainforests. Since the air lost its moisture here, the air leaving is very dry. So when you get to about 30 degrees in north and south, that air is so dry that there's not much rain there, and it causes bands of deserts. So I'm going to write that in. If you go through on the map looking at the United States and Mexico, across the ocean into the northern part of Africa, you'll notice desert areas all along 30 degrees north. Same for 30 degrees south. That air is very dry there. 60 degrees north, you'll notice hot air rising again, and you actually get another band of forests. They're not rainforests, but there are forests there. And same for 60 degrees south. There's not much land on 60 degrees south, but the land that is there is forested. So you've got a pattern: forest, desert, forest, desert, forest. So what do you think's here? It's not really desert like the Sahara, but it's an ice desert. Not much snow there and a whole lot of ice. So that area, even though it looks like it's just snowing there all the time, it's an ice desert going in with our pattern. So I'm going to write ice desert up here. So our planet has bands, latitudinal banding, because of the unequal heating of the Earth. So looking at a map, ignoring the ocean, you'll see desert, forest, desert, forest, desert, forest, desert. Super cool. Okay, now let's talk about the wind in each climate zone, getting back to our main topic. So in the polar climate zone, air is rushing from the North Pole to the equator, and it's actually going to not go straight south because the Earth is spinning. And the Earth is spinning faster at the equator than it is at the top, at the North Pole. The equator is much wider than it is at the North and South Pole, so it has to cover a larger distance in the same amount of time. So when the air is leaving in the northern hemisphere, it actually gets turned like this. So if you were that air going like this, you actually got to think about it. You're getting turned to the right. Air in the northern hemisphere turns to the right. So if you're headed like my pen is, you get turned to the right. And these winds are known as polar easterlies. Because they are going from east to west. I'm going to mark east on here. Oops. East and west. Because we generally talk about winds or name them from the direction in which they come from. So they're going from the east and they're headed west. In the southern hemisphere, the faster rotation of the Earth at the equator, this is called the Coriolis effect, it causes wind to get turned to the left. So imagine your wind trying to make it to the equator, you get turned to the left, turn to the left. Think about it like you're coming this way and you get turned to the left. And those are also known as polar easterlies. Lots of patterns here. Look for them. It'll make your life easier. And they're cool nature patterns. Polar easterlies. Now let's talk about the equator and tropical climate zones. We've got air rushing in towards the equator. Remember, these are our surface level wind airflow. And they get turned in certain directions depending on which hemisphere. So in the northern hemisphere, they get turned to the right. So they're headed this way and they get turned to the right like that. You gotta think about it. You're coming in this way and you get turned to the right. In the southern hemisphere, they get turned to the left. The wind does. And these are the prevailing winds of the tropical climate zone, and they are known as trade winds. They are called trade winds because they brought people from Africa and Europe to North America and South America. You could take, if you're on a boat with a sail, you could use those currents to get you to North and South America. Unless you get stuck at the equator, that rising air creates very little wind and it's really calm in this area. This area is known as the doldrums in the ocean, and ships would get stuck there. Same thing at 30 degrees north and 30 degrees south. All right, last global wind are our westerlies. So they're the oddballs again. They're moving north and they're moving south. Okay, so in the northern hemisphere, they get turned to the right. In the southern hemisphere, they get turned to the left. I always have to think about that. I was never good with my rights and lefts. So it's like you're going that way and you get turned to the left. And these are known as westerlies because they are coming from the west and they're going east. In the United States, westerlies are going to make the weather go from the west coast, like from the west side to the east side. Westerlies are very influential in our weather patterns in the United States. Trade winds will carry hurricanes from off the coast of Africa all the way to North and South America. So they're going this direction. Westerlies are also going to take warm air from the southern part, like not really the southern United States, but even further south all the way to Europe. So those are some global winds that we have. We've got polar easterlies, westerlies, and trade winds. You also have some nature patterns formed from them. Ice desert, forest, desert, forest, desert, forest, ice desert. So look at a map of Earth, look at all the different colors, see where you have greens and tans and greens and white, and you will know that it is because of the uneven heating of the Earth and our rotation. Nice job.